Hey everybody, this is Alex Merced and welcome to another video talking about data concepts. And in this video, what we're going to do is talk about data processing systems. So in the last video, we talked about data storage systems. Where do we put our data? But oftentimes we need to either do ETL work, which means move data from one place to another. And sometimes we need to do analytical work. So we need systems that process that data. Okay, and basically when we get to the world of big data, like oftentimes when we talk about just like a single like laptop, okay, so we think about like single node processing. So I got data on one computer and I'm just like analyzing it. Okay, oftentimes you're going to think about tools like probably most of it's going to be done through something called Excel for Microsoft or Google Sheets, where you just put the data into a spreadsheet and you can do a lot of analytics using like cell formulas and things like that. Okay, other popular tools for this can be like using SQLite 3, like we did in the intro with SQL videos, where you can really just kind of like load up data into a database right there on your computer and work with it. More recently, another alternative for that, DuckDB, has become pretty popular for that as well. On top of that, there's like pandas and polars, which are again great data frame libraries in Python, where you can just load up data and work with it right there from your computer. Okay, and oftentimes a lot of this is all done through Jupyter notebooks, okay, which we'll cover later on. But what happens when you're dealing with a distributed environment? Okay, again, when you have a situation where you have lots of nodes. Okay, so let's draw some nodes. Okay, because the reason is the data that you're working with is huge and doesn't fit on one computer. So then what you need is what's referred to as an MPP system, massively parallel processing, which just means being able to essentially break up that work across multiple computers to handle much larger data sets. Okay, so with the advent of a massively distributed storage in Hadoop, along with it came a massively parallel distributed processing system, and that was known as MapReduce. Okay, so this was essentially, and it lives up to its name. Okay, when you think about what map means, like if you've ever done programming and use map often takes a list of items and allows you to do something to each item individually. Okay, so essentially, so when you think about that in the context of MapReduce, I would take a chunk of the data, pass it to each node, and allow that node to do its part of the job. Now, reduce is the part, if you again worked with like programming and functions, especially functional programming, reduce allows you to take a list of values and reduce them into one single value. So of course I would then take the results from each node, build out create one full result set, reduce it to a result set that would then be passed back as the result. So thus the name itself kind of describes sort of its architecture. Okay. It would map and reduce. Okay. But the thing is that in order to write a MapReduce job, is you'd have to write the jobs in Java. Okay, and Java isn't the most accessible for the if you weren't trained in developing in Java, Java is not going to come super naturally to you. Let's put it that way. And it could be very, very verbose. So you basically be writing these jobs where you're saying, okay, hey, let me go start go grab data from point A, and let me go load it over here, and let me go make these transformations to it, etc., etc., etc. And then basically what made it a little even slower is that every time you made a transformation to the data, or you sort of completed some sort of task, what would happen is that it would then have to write to disk. So essentially, you would do a thing, and then it would update the Hadoop file system with the data. So you had these two problems. One, I had to write jobs in Java, and two, it was slow because it was constantly writing to disk after like ever so often. Okay, after every job. Okay, which would again, the process of writing a large amount of data to disk before you do the next job can be quite expensive. Okay, as far as time. So what was the solution to this? Well, the solution to the Java piece was something called Hive. And what Hive it does, and we can call that, we might as well call it Apache Hive because it is an Apache project. Apache is just a foundation that houses open source projects. So those open source projects may or may not be related. They're just projects that meet certain thresholds of sort of community governance and community run, and then they become part of the Apache portfolio of projects. Okay. But if we take a look over here, Apache Hive, what it does, it allows you to write SQL, then converts that SQL into MapReduce. At least that's what it originally did. Okay, nowadays you can convert it to other things, but the idea is it allows you to write SQL and convert it into some other the imperative code for some other processing network. Okay, so that's what Hive did. Okay, and that made life a lot easier. So it made it a lot easier to write MapReduce jobs, but you still had the problem where it wrote to disk after, ever so often. And that slows down the job, having to constantly just write to the storage. Okay, so eventually what happens is you end up creating Apache Spark. Apache Spark hits the stage. Now Apache Spark is written in Scala, which is another language that is used on the Java virtual machine. And I'll probably do a video on the Java virtual machine just to kind of appreciate sort of the role of Java, Scala, and sort of the deal there. Okay, so Apache Spark. In Apache Spark, you could write jobs in Java or Scala. Later on, they came out with a Python way of writing Spark jobs. But the benefit of Spark is that, it can use memory instead of writing to disk every time. What does that mean? So let's say I have like 10 steps to a job. Instead of updating the storage between each step, okay, which is again where MapReduce was taking a long time, Apache Spark could just hold the results in memory, do the next step, and not write to disk till the end. Okay, so basically you wait till you get the final result after all the steps. In that case, you could really speed up the processing. Okay, and then the processing that data a lot more intelligently. Okay, so basically just made much better use of sort of in-memory storage between tasks. Okay, so Apache Spark became sort of like the de facto standard. So like instead of using Apache Spark, a MapReduce to handle jobs in your Hadoop storage, you would use Apache Spark, and Apache Spark could also be used on any storage layer. So you could use Apache Spark over your object storage, and it just became sort of the de facto way you did a lot of data engineering work, especially particularly ETL work, meaning moving data from point A to point B, and all the steps you need to do to get that data not only in the new location, but in the form that you want it. So that means like denormalizing that data, cleaning the data, validating the data, all this kind of stuff. And so that became sort of the de facto standard. But again, you still have to kind of write imperative code. It did have a SQL API, but not necessarily like always the most convenient thing to use, because you still have to like, it's not like you can just, it wasn't necessarily built for raw consumer inline analytics. Like you could do that, but it wasn't necessarily like, its bread and butter was really like ETL. Like it made it really easy to write really, and we'll work with Apache Spark so you can in future videos so you can see it at work. And another massively parallel, so basically what happens is that you still ended up moving a lot of your data to the data warehouse, because the data warehouse was still just an easier place to do a lot of work, okay, because it was just, you had this nice big platform. And that leads us to the last massively parallel system we're going to talk about today, which is Dremio. Okay, so Dremio creates another massively parallel processing engine that is Arrow-based. Okay, so it's able to be extra fast because you're using Apache Arrow for processing. Okay, so it's very optimized for working with Apache Arrow and Parquet files to get really, really kind of fast performance. It's going to leverage another project called Iceberg, which I'll talk about in a separate video. And basically, by leveraging these technologies, it's able to be really, really fast. Okay, but also it's really easy to use. So the idea is it's a fast, fast engine. So you oftentimes these massively processing the software that massively processes data across multiple computers are oftentimes referred to as engines. Okay, they basically they are the programming that then executes a job. They are the engine of getting the thing done. But it's a fast engine and easy to use because another part of Dremio is the UI. Okay, so it's very SQL focused. So instead of using like Java and Scala sort of this or Python as its primary way of talking to the data, like Apache Spark, it uses SQL as the primary sort of way you talk to your data, okay, and do work with your data. So it's very SQL focused with a very user-friendly UI. Okay, so you have this nice place. If you've done some of the Dremio videos I've done in the past, you've seen that it has a really nice interface that makes it really easy to organize and distribute your data. So this kind of gave that massive. So basically now when I want to give access to the data on my Hadoop cluster or my object storage and give it to my end users and give them an easy way to use the data that's also fast, Dremio's kind of filled like that space. So a lot of times what you see nowadays is that people have their data in Hadoop storage or in object storage, and when they need to move data into those storage layers, they'll use Apache Spark for the ETL work. And then when they need to give that data for analytical uses to their data analysts and data scientists or to their partners and to other stakeholders, they'll use Dremio as that delivery layer. Okay. But all of these are massively parallel systems where they're distributing the work across several nodes. Okay, each one sort of improves in their way. So again, Apache Spark improved over MapReduce by basically taking advantage of not writing the disk after every step. Dremio improved upon that by really leveraging things like Apache Arrow, Apache Parquet, Iceberg. There's a lot of other sort of optimizations that exist under the hood and its caching layers, and providing an easy to use UI, making that massively parallel engine more accessible to non-technical users. So that way they can use that massively parallel processing power without having to be necessarily a Java or Scala expert. And actually being able to do some ETL, a lot of ETL work with Dremio, because you can connect multiple sources and then use SQL to move data around. But with that, that hopefully gives you a better idea of what is a massively parallel processing system. Again, it's just a software that uses multiple computers to do computing work. Okay, these are some of the big names in that space and sort of their role in the big picture. But hopefully you guys enjoy that. My name is Alex Merced. I'll see you later on. Make sure to like, subscribe, and leave a comment. I'll see you all later.